Electrostatic notes. If I rub a balloon with some fur, I'm going to build up a static charge onto it, and that balloon can stick to the wall. This is due to an electrostatic force. Electro as in electricity, and static means not moving. We're building up charges, and the charges just sit on the balloon and they're not moving. So we'll start off by defining what is this electric charge. Electric charge has the symbol big Q or small q, and it's measured in the units of coulombs. It can be positive or negative. When I'm rubbing the balloon with the fur, the balloon was losing electrons, so it became positive charged, and the fur then was gaining electrons, it became negatively charged. The charge of an electron is minus 1.602 times 10 to the minus 19 coulombs. This is a number that you'll probably have memorized. We use it quite a bit. It's also on the back side of your formula sheet, so you don't need to memorize it. The charge for a proton has to be equal and opposite to that, so the value is the same, but the charge is positive instead of negative. Remember, in the atoms, the protons and electrons are in pairs and cancel each other out, so it makes a neutral charged atom. So how many electrons would be on that balloon? Let's say the charge on this balloon was 3.2 microcoulombs. Micro is one of these metric prefixes we should have memorized. It stands for 10 to the minus 6 power. So instead of doing a unit conversion from microcoulombs to coulombs, we just substitute times 10 to the minus 6 in place of the micro sign. Then I'm going to use a unit conversion with the number up here. We're canceling the coulombs, so it goes in the bottom, and then electrons goes in the top. Dividing, we get 2 times 10 to the 13 power electrons, and because the balloon is positively charged, that means it's missing those electrons. It also means that the fur gained this many electrons. It has a negative charge. Coulomb's law tells how strong that force is between the balloon and the wall, or between two charged particles. So let's look at another example. Let's say I have two different balloons here. One has a charge of positive 5 microcoulombs. The other one has a charge of negative 7 microcoulombs, and they're a distance apart from each other. Coulomb's law is just a formula, kQq over r squared, and it's to calculate the force between those two charged particles. K is a constant. It's called Coulomb's constant. Big surprise. And this number is also on your formula sheet. We often round this first number just up to 9, so it's 9 times 10 to the 9, or you can use the full value if you want. Now, the electric force here follows the inverse square law. The inverse square law is not only true for the electric force, but for the gravity force, the electric force, the magnetic force, light waves, and sound waves all follow the inverse square law. So, quick explanation of the inverse square law. If I take a light and shine it on an object, the brightness of the light, we'll call it the intensity of the light. Intensity could also be how loud the sound waves are. It could be how strong the magnetic or electric or gravity field are. And this intensity is proportional to 1 over the square of the distance. So if I double my distance, if I put 2 down here in the denominator, I get 2 squared, I end up with 1/4 of the intensity. So the light is going to be 1/4 the brightness, the sound is going to be 1/4 the loudness, or the strength of the magnetic or electric or gravitational force would be 1/4. Or if I triple my distance, 1 over 3 squared makes 1 over 9, it would be 1/9 as intense. All right, so back to our notes here. When we're plugging the numbers into the formula, we have to remember to put in 10 to the minus 6 for both of the micros and both of the charges. And since the distance is measured in centimeters, I'm putting in 10 to the minus 2 in place of c. So we get meters to cancel with meters squared in the units. And notice that I did not put in the plus or minus signs. This formula only tells us the value or the magnitude of that force, not the direction of the force. So make a note here. The formula gives the magnitude of the force. The direction is going to be along the line between the two charges, so it'll be a horizontal. And we use the rule opposites attract or likes repel to tell the direction of the force. So this is the same rule for electric charges that it is for magnets. The opposite poles, north and south, are going to attract each other, where like poles, south and south, are going to repel each other and push away. So on our problem, we have plus and minus. These are opposite charges, so they are going to attract each other. So I'll say my net force is 1,400 newtons towards each other. This one gets pulled to the right, and this one gets pulled to the left. Let's do another example problem. This one has 3 different charged particles, and we're going to find the net force on object A. So object A is being pulled by object B, and it's being pushed by object C. So there's 2 forces involved here. So we'll look at the first force, just the force from object B. We're using Coulomb's law, KQQ over R squared. Remember to substitute 10 to the minus 6 for the micro. We're not using plus or minus signs. And this comes out to 135 newtons for the value. For the direction, we're going to see that these are opposite signs, so they attract each other. So A is going to be attracted to B with a force of 35 newtons to the right. And Newton's third law tells us that B is going to be attracted to A with the same force, 135 newtons, but in the opposite direction to the left. So I'm not going to label these two on our picture today because we're just looking for the net force on object A. The other thing that's putting force on A is object C, so we'll calculate that next and ignore B for now. So using Coulomb's law here, again, I'm not using the minus sign. We have to put in 10 to the minus 6 for the micros. Look at the denominator here, though. The formula wants the distance between objects A and C, but they didn't show us that number on the diagram. On the AP test, they're going to go out of your way to show you a picture like this because they're going to try to mess you up and see how many people plug in the 0.20 down here. The distance from A to C is 0.30, so always pay close attention to our definitions here. So this one comes out to be 20 newtons, and this one, these are both negative charges. They have the same charges. They're going to repel each other. So C is going to push A to the left, and A is going to push C to the right. And again, we only want the force on A. So looking at both of the forces on A, object B pulls it to the right, object C pushes it to the left. We're going to do the vector sum of these 2 forces. When we do vector sum in a straight line, we do forward minus backwards. And that way when the answer comes out positive, we know it's to the right, or if the answer comes out negative, we know it's to the left. So our final answer is 150 newtons to the right. In the AP2 class, they'll arrange the charges more in a triangle. We see 1 and 2 have the same charge, so 1 is going to push 2 in this direction. 2 and 3 have opposite charges, so 2 is going to be attracted to 3 in this direction. So we have to find the net force between these two. We're going to have to do vector addition, which is using the Pythagorean theorem with those 2 forces. End of notes.